Let's just check something. Okay. Speed of reactions. Speed of reactions. Which is energetics. Speed of reactions. Speed of reactions. I think we can start. So when you talk of speed of reactions, we are measuring the rate of a reaction. The rate of a reaction. So what do you understand when I say the rate of a reaction? What am I talking about? The rate of a reaction. What are we talking about? The rate of a reaction is simply a measure. So it's a measure of how quickly. Yes. How quickly the reactants. Yes, the reactants are used up. How quickly the reactants are used up, or a product is formed, or how quickly a product is formed. Are we together there?
Yes, sir.
The rate of a reaction is simply it's a measure of how quickly the reactants are used up, or how quickly a product is formed. So now in chemistry, there are factors that affect that. So now let's look at what they call the kinetic or the collision theory. The collision theory. Maybe let's use a new page to explain this properly. The collision theory, what it states, which you are required to know. Collision theory. So maybe I'll use A plus B. So A plus B is just standing for anything. When they react, let's say they form C plus D. Okay, this is just an example, okay? So I'm sure that you know that these are your products and in chemistry, and these are your reactants because they have to react to form C and D. Are we together? Now, maybe for some of you, if you have never done this in school, you simply think when A and B collide, then something is formed. But that's not true. Are we together? So what the collision theory states, that maybe if you want to summarize it, is that when particles collide, in this case, it's A and B. When particles collide, are we together? When the particles of the reactants collide, okay, what will happen? When particles of a reactants, two things will happen. When particles collide with each other, they can only form someone's volume there. They can only form a new product. Someone can the volume there. The volume on someone, I think one of you there.
It's not my mouth.
Okay, that's fine. Let's do this so that it doesn't affect the recording of the lesson. Let's mute all for now. Okay, now for the benefit of everyone. So when particles react, A and B, they can only, there are two things that can happen. When they react, they can only form a product if they have sufficient energy. Are we together? When particles react, A and B react, they can only form C and D if they have sufficient energy. When particles react, let's see if that issue has been fixed. I hope they've worked on that. So, no, they haven't worked on that, so unfortunately, I have to mute everyone because it affects the whole lesson there. So we're saying if A and B collide, they can only form products C and or D and C if they have sufficient energy. Sufficient energy, known as activation energy. Energy. That's the only way that they can form a new product is if they have that's sufficient energy. So sufficient activation energy is the minimum energy that reactants require for them to be able to have a successful collision. Okay. So successful collision is when A and B have the minimum energy, which you call sufficient energy. But if they don't have the minimum energy, they simply bounce back altogether. So if they don't have, you can summarize that, if they don't have the sufficient energy, they don't meet that requirement of sufficient energy, they simply bounce back. And we call those unsuccessful collisions. So if they don't have enough energy, they simply bounce back, and we call those unsuccessful collisions. In reality, in any experiments, we have more unsuccessful collisions than successful collisions. Is that clear so far? I think that is straightforward. Let's see. Maybe they've sorted their issues there. So we're saying in reality, we have more unsuccessful collisions than successful collisions. Are we together?
Yes, sir.
Okay. So that's your kinetic theory. That's what you need to remember. Now, so what factors affect, let's look at factors that affect a reaction, a chemical reaction. A reaction or chemical reaction. What are the factors that affect a chemical reaction? There are 4 of them. Temperature, a catalyst, a temperature, a catalyst, concentration.
Surface area.
So concentration is mainly to do with acids. We'll talk about it just now. And the surface area is to do with solids. All together. Temperature, catalysts. Those are the factors that affect a chemical reaction. Is that clear?
Yes, sir.
Let's explain them in detail. Let's start with temperature. Remember, I talked about the reaction. Maybe temperature. Maybe I need to show you something which is not there from O level. Anyway, so in general, sometimes, okay, for A level, they will show you a graph which is called the Boltzmann. It's not there for A level, but it will help us to explain certain things there. So this is the energy. So this is maybe my activation energies here. So this is, so most of your energy, this is the average particle energy. So average particle energy. You don't need to know this graph. Okay. So most, it means if it's the average, it means most particles have got this energy altogether. But they don't have the sufficient energy for the reaction to take what? To take place, which is the activation energy. You only have a few particles with enough energy for the reaction to take place. Okay. So if I increase temperature, let's see what happens if we increase temperature. What do you think happens if we increase temperature? So let's use the same scenario where we said reactants A plus B forming C plus D. If I increase temperature, what happens to these particles? Use your physics, your chemistry. What happens when you increase temperature?
the substance will melt. Is that so?
No, if we increase
Will
temperature,
break.
we don't know whether it's solids or what. But in general, if I increase temperature, what happens to the particles? They gain what?
Energy.
They gain kinetic energy. If I increase temperature, that's what I was looking for. They gain kinetic energy. So if we increase temperature, they gain, the reactants gain kinetic energy. Gain more kinetic energy. They gain more kinetic energy. So when they gain more kinetic energy, it increases what? The rate of collisions. Increases the rate of collisions. Collisions of A and B, or reactants in general. Reactants. Are we together? So it increases the rate of collisions. When it increases the rate of collisions, it means we are going to have more particles with sufficient, we are going to have more, it increases the chance of successful collisions. Are we together? So when we do that, it also increases the chance of successful collisions. Okay. Increase the temperature. We have increased the temperature. So if I increase the temperature, if I was using this graph, this graph will shift like this. Something like this. Are we together?
Yes,
we now have more particles with average energy. Also the activation energy, more particles with enough activation energy for the reaction to take place. Is that clear with everyone there? When I increase the temperature, the particles gain more kinetic energy, more collisions. When they collide more, it increases it means there's higher probability of more successful collisions altogether. Okay, that's how temperature affects increasing temperature. Decreasing temperature is the opposite. It reduces the rate of a reaction. Okay. Now, let's look at concentration. Concentration. And maybe we explain what we mean by concentration. So remember I said it's mainly to do with an acid. If I have 0.2 moles of, the reason why I'm saying an acid, because an acid, if you go and read that topic, is useless as long as it's not in water. Are we together? So we talk of concentrations of acids in water. So if I say 0.2 moles of sulfuric acid, we want to use this as an example to explain this. Then let's say I have 0.5 moles of per cubic decimeter of sulfuric acid. Then I have 10 moles per cubic decimeter of sulfuric acid. Now, what this simply means is that in 1 cubic decimeter of a solution, in one, which is volume, in 1 cubic decimeter volume, I have what? How many moles of the acid? I have 0.1 moles of the acid. That's what it means. This means I have 0.5 moles in also 1 cube. So the volume is the same. So this is a more concentrated solution than the other two. This is 1, 2, 3. So the number 3 there is a more concentrated solution. Are we together? Because it has more moles per unit volume. Are we together? So how this affects or increases, so if I increase concentration, if we increase concentration, if we increase concentration, are we together? If we increase concentration, it means I now have more concentration of the what? If it was the acid, I now have more concentration of the acid per unit volume. So if I now have more concentration of the acid per unit volume, I'm going to have more what? I'm going to have chances of more successful collisions. Can you see that? Because indirectly, I have increased the number of collisions altogether, because I now have more moles of the acid per volume compared to this. So this one, we're going to have more collisions than this. This will have more collisions than this altogether. So increasing the concentration, that's how it increases the rate of the reaction. Okay. Notice now, sometimes they say, if I increase the volume of an acid, I have not necessarily increased the what? The concentration. Are we together? You have to be very careful there, because when I increase volume, so look at this. Volume, remember we're saying more per cubic decimeter. If I'm increasing volume of an acid or a solution, I am increasing this. But it doesn't mean the number of moles have increased. Are we together? So you have to be careful with questions, because sometimes they talk of increasing volume. Increasing volume does not imply that a reaction can speed up. Are we together? It's only when we have increased the concentration, the number of moles per unit volume. That's when we increase the rate of a reaction, which is to deal with acids. Now let's talk of a catalyst. A catalyst. So with a catalyst now, if I was to show you the same graph that I showed you, which I call the maximum Boltzmann graph. Now, we just said the activation energy. If I use a catalyst, there are certain things that, so how does a catalyst, who knows how does a catalyst speed up a chemical reaction? How does it do that? How does a catalyst, yes, what do you think? Does it increase the rate of collisions? How does it work? A catalyst. So a catalyst lowers this activation energy. How do you get that? A catalyst lowers the activation energy. Lowers or provides lowers the activation energy. Energy. So if it lowers the activation energy, what does that mean? It means I now have more, even in the same concentrations, I now have more what? More, yeah, now it increases the chance, because I now have more particles with sufficient energy. Are we together?
Energy.
For them
Yes,
to
sir.
react. So it lowers the activation energy, which means now we increase the probability of particles with sufficient energy. So it means we increase the probability of reactants with sufficient energy. Are we together then? Clear? Then the last thing is the surface area. And I said this is mainly to deal with solids. Because in a lab, I'm sure some of you that have the privileges of lab in your, they mainly talk of the carbonates, especially calcium carbonate, which can be like some small stones, grains like this. And you can also crush this to fine powder. Is that true? So how is surface area? How does it affect the reaction in general? What did increasing the surface area of a solid? How does it affect? Can someone explain to us? Why does it increase?
It
I can't hear
increasing
you.
the surface area exposes more of its particles to attack.
Yes, so it will increase your frequency of collisions. Okay, yes, because when you increase the surface area like this, you are increasing, for example, if it's calcium carbonate. So that reactant there, when you increase its surface area like this, you are exposing it more to the other reactant to act on it. So it means I'm going to have more collisions than I had before when I was using. How together then? Is that clear then? That's how it affects a chemical reaction. Now let's talk of some of the reaction graphs just now. The graphs. I'm going to use one graph. Then we analyze one graph. But you can have different graphs. For now, I'll start with this. So let's say this is my time and this is my rate of reaction. Then I've got something like that. Then I have something like that. So this is curve A, this is curve C, this is curve A. Are we together? Clear with everyone?
Yes, sir.
Now, we want to apply everything we have talked about. Catalysts on the same graph. Catalysts, temperature, concentration, and surface area on the same graph. Now, there are certain things that I want to ask you there. Which reaction is faster, C or A? Charmaine, which reaction is faster, C or A? What do you think? Remember, this is time. Which reaction is faster? Now, my question is, where is reaction C stopping? Just describe, where is this reaction stopping? Where is it stopping? Remember, this is the red, like this. When the line becomes what? Okay, like this. Maybe I have not drawn it correctly. So when the line becomes straight, like this, this reaction is stopping there. The moment it becomes, now it's constant. Are we together? This reaction is stopping where? There. Are we together? I hope it's clear with everyone. Because the reactants are being then there's nothing happening. The rate of the reaction is now just the same constant because the reactants have been used up. And this reaction A is only stopping there. T2. So A takes longer. Are we together?
Yes, sir.
Than C. So if they'd asked for which one do you suggest a catalyst was added, a catalyst speeds up a chemical reaction. So which one? C. C, because it's taking what? It's taking short time for the reactants to be used up. Is that clear? Or it's not clear?
Yes. No, it's clear.
Clear with everyone? I hope it's clear then. Okay, so it means if they'd asked for a catalyst, this one used a catalyst. If they asked for a temperature, which of the two do you think temperature was increased? This one is taking short time, so TC again, temperature. So this one is higher temperature. This one is low temperature. Are we together? If we had looked for a concentration, increase in concentration, increase the rate of reaction. This one is higher concentration. This one is lower concentration. Are we together? Notice we can only investigate one at a time. I'm just saying if it was the same graph. They're asking for a surface area. This one will have greater surface area. Greater surface area. So it means e.g. powder. And this one is low surface, small surface. I mean, so it has a small surface area, it doesn't have a greater surface area. So it can be lumps of your calcium carbonate. I hope it's clear now with everyone, or it's not yet clear. It's fine, we'll look at questions next lesson. Now, how do we measure? Now we want to look at the practical aspect of this topic. How do we measure rates of reactions? How do we measure rates of reaction? So maybe as a subheading, how do we measure rates of reaction? How do we do that? The rates of reaction. So measuring rates of reaction. Measuring as a heading. Measuring rates of reaction.
So at school, I think the experiment will be like adding like different substance to like a liquid, and then when you change the color, that's like
Now it depends on the question.
Or...
Okay. Yes, I get you. It depends on the question. Let's say we want to measure, we want to prove that surface area, let's start from there, affects rate of a reaction. We want to prove in a lab that surface area affects my rate of reaction. So what I'm going to use, I have to use equal volume, number one, equal volume, in fact, equal concentration. Let's not talk about equal volume. Equal concentration, but that's not what I'm investigating. Equal concentration of hydrochloric acid. All together. Equal concentration of the hydrochloric acid in two setups. Okay, in two setups. We use equal concentration of hydrochloric acid. Equal concentrations of dilute, because it only works when it's dilute, of dilute hydrochloric acid, number one. Number two, now we have to use same mass, so we have to measure the mass. Same mass of calcium carbonate, which is white. You've seen that in labs. Lumps. Okay, 10 minutes left. Maybe we'll look at this as the last, then we'll continue from there. So we're saying calcium carbonate lumps, same mass of calcium, and another setup with same mass of powder. Are we together? Of your calcium carbonate. I'm sure you see what we are trying to investigate. Remember? Same mass, but the other one are lumps. The other one is what? The powder. Remember, the experiment has to be fair. Okay. Now, what else do you need? You need a stopwatch. So these reactions, remember, you need to time them. You can do them separately. So you can start with this one, then we start with this one. But we are doing them under the same what? It's only what we are investigating under the same time. So we need the stop. Are we together? Make sense?
Yes, sir.
So what you simply do, you have measured the volume of your lumps, your calcium carbonate, you've measured, the masses, they are the same. Then you pour out in one beaker, you pour out what? Your calcium carbonate, if you want. But normally what you start with anyway is the acid. That you use a pipette. Then you put equal volumes into different beakers of the dilute acid. Okay, into different setups. altogether, or you do one setup at a time. Then you're going to add what? A certain mass of your calcium carbonate altogether, lamps. Then you do the same for the other setup. Okay, the steps are the same. Then when you have done that, remember you want to make sure that, remember your reaction, so you've used data. Then how are we going to investigate? Because remember, we want to prove that surface area affects the rate of a reaction. How are we going to do this setup? What is formed when a carbonate reacts with an acid? It forms a salt, who remembers? Salt plus water plus carbon dioxide. So how do we investigate this setup? There are two ways. You can compare the masses, mass loss. Why is there a mass loss? Because carbon dioxide is being given off, and you are using a conical flask or a beaker that is open. So if this is open, the carbon dioxide is given off, so there is a loss in mass. So whether it's 2 minutes or whether it's 10 minutes, you are measuring the mass before, then you are measuring the mass per interval. Are we together? So you are measuring the loss of mass per interval so that you can compare the two reactions, the one with lumps and the one with powder. I hope it's clear with everyone. Carbon dioxide being given off, so there's a loss of mass. What could we do if we want to measure? So we can also measure number one, the mass loss. Number two, we can also measure the volume of carbon dioxide produced, compare per interval. But now this is where, how do we close this? How do you now improve this setup? If we want to, we can't use a beaker. Can you see that? We can now use a conical what? A conical flask. Then we have to cover it on top. We don't want any carbon dioxide to be lost. Then there I have a what? A syringe, a gas syringe, so that I measure the carbon dioxide that is produced per minute or per 30 seconds when this is taking place altogether. Then I can compare between the powder and the lumps. Is that clear? The rate of reaction? I hope it's clear with everyone.
Yes, sir.
That's how we can do that. So number one, you can measure the mass, because we're saying the mass, this is open. So the carbon dioxide is being lost, so that it causes a reduction in mass. So at least we expect the fine powder to have a greater loss of mass per minute, compared to whatever time interval you are measuring, compared to this one. If we are measuring now, if you close this so that no carbon dioxide escapes, then the gas syringe will start recording the volume of carbon dioxide being produced. You expect the powder, because it's a large surface area, to have what? To have more volume of carbon dioxide being produced per unit time. But remember, the acid concentration has to be the same. Everything else has to be the same. Clear on that? I think we've tried to make it very, very clear there. Okay, so go and read more on that. We will look at 2 more experiments the next chemistry lesson. I think that is tomorrow, on measuring rates of reactions. All right, together?
Yes, sir.
Then we'll look at questions. Okay. We'll see you for bio just now.